All right, so today we are going to use what we call the integrating factor approach to solve a special type of ODEs. Notice this ODE is linear and it is non-homogeneous, and you don't have constant coefficients. So this is a constant, but this is not a constant. So not every time you don't have constant coefficients, you have to use the integrating factors. The ODE has to look of this form. Now, if you have a function of t here, you can divide across, and that's fine. Notice that this is a first order as well. So if you have an ODE of this type, there is a clever way to solve them. The first thing I'm going to do is I'm just going to show you how it works very quickly, and then I'm going to show you why it works the way it does. So I want to work out an example first so you get familiar with the approach. If you look at the left-hand side, you see that the derivative of y is here, and you wish that this would be the derivative of something in here. Because if that is the case, then this looks like the product rule. That's how the idea came about. So that piece that we need across the board, it's called the integrating factor, is e to the integral of p of t dt. Sometimes we call it mu of t, okay? So we are going to work out an example first to see how it works, and then we will talk about why this, and can we take even a better shortcut, okay? So here is an example. I actually picked this from your book. Y prime plus p of t y equals q of t. This is like the forcing term, r of t. We used to call it r of t. So if you look at the integrating factor, you're going to have e to the p of t dt, which is e to the natural log of t squared, which is just t squared. Now, I know you could say, well, shouldn't we have a constant since we're integrating? Yes, you can. But we're only looking for the integrating factor. We're looking for one factor that will allow us to do the job on this one, which means on this one. So if I multiply across the board by t squared, I get t squared y prime plus 2 over t times t squared, which is 2t y, plus this times t squared, okay? Now you see that the derivative of y is sitting here, and the integral of 2t is sitting here, which means that the derivative of t squared is here, and the derivative of y is here. So this is no more than y t squared prime, which equals that as well. Now we integrate both sides. The left-hand side remains the same, and the right-hand side, you get this minus that dt. You integrate both sides. You integrate this side, you get 1/4 t to the 4th minus 1/3 t cubed plus a constant now, because we're looking for a general solution. And then you divide by t squared. I want to give you a warning here while I'm in here. What you don't want to do, so you have y t squared equals the integral of t cubed minus t squared dt, this one. You don't have the right to cancel t squared because this is inside an integral and this is not. So please don't turn this left-hand side, this side, into y equals the integral of t minus 1 dt. You don't have the rights to do that, okay? So I found my solution, right? I found my solution. It's weird that the c is being divided by t squared, but that's what it is, okay? So feel free to differentiate this and dump it here and multiply this by 2 over t and see if you get t minus 1. It should work out, okay? So I'm going to skip step 2 for a moment, page 2, and I'm going to go back to why did we choose to multiply this equation or this equation by the integrating factor. Where is this coming from? Where is this coming from? So it's actually simple. So we begin with our general ODE, and what are we going to do is we're going to multiply everything by mu of t. We don't know what mu of t is yet, but I'm trying to multiply by mu of t in such a way that this becomes like the product rule, okay? So I'm just multiplying by mu of t, and I cleaned up the mess. I'm not going to write mu of t, I'm just going to write mu. Instead of p of t, just write p, and q of t, q, and mu of t. It just looks a little cleaner, okay? So all of these are functions of t. All right, so the question is, find mu. We're trying to find mu such that mu y prime is this, okay? Now we know from the product rule from calculus, mu y prime is mu prime y minus mu y prime. And all I'm trying to say is this. F g prime is f prime g plus f g prime, like that. So if that, by definition, is this, and we are trying to find mu so that this equals that, so we're going to force these two to be equal, okay? That's what I wrote here, okay? So mu y prime, mu prime y plus mu y prime, here it is, equals mu y prime plus mu py. Mu y prime cancels, and mu cancels. So now you have mu prime equals mu p. I'm going to integrate by separation of variables, divide by mu, and integrate both sides. You get natural log of mu, because the derivative of the bottom is at the top, so that's triggers natural log of the absolute value of mu, equals the integral of p. We don't know what p is, so we're just going to leave it at that. So that gives me mu of t equals e to this function, right? And that should end the story. This is the integrating factor. I use QED. It's a Latin symbol or expression. I call it quite elegantly done, right? Or what did I used to say? Question every detail. How about that? Okay. So now we know why you multiply by this, okay? So now you can always do that. And we'll work out a simple example at the end, maybe. Okay, so now I want to show you a quick shortcut on how do you avoid going through this entire process. How can we avoid? I mean, you still would need to know what this is, but you don't want to go through the steps. You want to go from the ODE directly to the solution, but you still need to know this, but you don't have to go through all of these, okay? So, sorry, not those, but these. You don't have to go through all of these steps. You can go from here to here, so long you know that mu of t happens to be t squared. If you know that mu of t is t squared, you can go from here to basically here or here, okay? So let's do that. So again, this is my ODE. Multiply across by mu. And so what do we want? This is the trick now. Let's assume there is a function mu so that its derivative if the product is the product of mu y. Okay? So that says that mu y prime has to be this, which has to be that. Which means, if you look just here now, these two terms, mu y is the integral of mu q. So that means y is 1 over mu q. Again, don't cancel mu, please, okay? This mu of t is inside the integral, and this mu of t is outside. So that means my general solution, y of t, is just 1 over mu of t, integral of mu of t, q of t. So let's work out the same example we had before. My function was this, okay? And my mu of t was t squared. So I can very quickly get the solution. So my solution, I should write it down. My solution is 1 over mu of t, remember mu of t is t squared, times the integral of t squared q of t. Q of t happens to be t minus 1. Okay? So I jumped, right? So long I know my ODE, I can jump to y of t. You still have to do some integration, but at least you skip some steps. Once again, please don't cancel t squared, okay? So y of t is 1 over t squared, and the integral of this, you've got to distribute first, and then integrate both pieces, and then, of course, now these are all the same. You could cancel t squared, okay? You get 1/4 t squared minus 1/3 t cubed over t squared, which is t, plus c over t squared, which is exactly what we got here, okay? So that's cool. It just allows you to skip some steps, okay? So the solution, if you want to use the integrating factor, will always be this, okay? Still need to find mu of t, and you may have a hard time integrating this, by the way. It's not necessarily easy, okay? I should work out an example right now, actually. Let's do that. So let's say I have, I don't know, y prime plus 1 over xy, I'm using x instead of t if you don't mind, equals, I don't know, 1. I'm making it simple, okay? So the integrating factor is e to the integral of 1 over x dx. You wonder why I picked 1 over x, okay? So that is just x, okay? So if I multiply across the board by x, I get this, and so that is xy prime plus y equals x, and that is a product rule, because the derivative, sorry, there is no prime here. The derivative of y is here, and the derivative of x is 1, which is here. So that is just xy prime equals x. Okay, you integrate both sides. You get xy equals the integral of x dx. So that means y is 1 over x, and then half x squared plus c, right? So y is half x plus c over x. It works out nicely. I could take the shortcuts, and the shortcut was y equals 1 over mu integral of mu q, if you remember. So mu happens to be the integrating factor, which is x, so that's 1 over x. And mu is x, and q happens to be 1. And dx, and that is the same thing as this. Oops, excuse me, same thing as that, okay? So you just finish. Now, as I said, it's not always easy. So let's say I have y prime plus x y equals, it doesn't matter what I write here. Let's write x squared, okay? So now it's a little difficult because the integrating factor is this, which happens to be e to the half x squared, right? Do you agree? So that is mu of x. So now if I multiply both sides by this, x squared, half x squared, okay? Now this turns out to be very nice, because the derivative of y is here, And the derivative of this is this times the derivative of that, which is x, which is here. So the left-hand side is cute. It's just e half x squared y prime. And the right-hand side, which is q of x times mu of x, right, is this. Now, if I integrate both sides, the left-hand side is done. Excuse me. The left-hand side is done. There is nothing to do. And I am in a big trouble here, right? So it's not easy to integrate this function here, because the derivative of half x squared is just x, but I have an x squared and I'm stuck, okay? So just because the left-hand side looks nice, it doesn't mean that the right-hand side is going to be helpful. If I had an x here, it would have been a little nice. But because, in fact, even if I had one, you wouldn't have x squared, right? And this is not easy. I mean, it's doable. I don't know if you remember from calculus. You have to use polar coordinates here. This is not easy. This one, don't worry about the half yet. This can turn out to be this, actually. Sorry, dx. It's a double integration. It's not easy, but it's doable. You can use, for this one, if you have an x here, it's also doable. If you don't have an x, you have to think of this, and there are conditions on why you could go from here to here. So it's not easy, but it's doable. Even though the ODE was not looking really bad, right? So let me erase this page. You don't need it. I was just working out an example. So I'm going to go back, if you don't mind. We started here. I did an example. And I want to show you that sometimes, like for this particular example, you can use, this is non-homogeneous. I know this is not a constant, but it's doable. So if you look at it here, I'm going to review with you how we handled non-homogeneous equations. I know we did constant coefficients, but this is not a constant, unfortunately. So if you remember, there is the homogeneous piece first. That's step one. And you can just separate the variables here. Okay, integrate both sides. I got this. Okay, so that's homogeneous if this turn out to be just c t to the negative 2, which is c over t squared, which is exactly this piece. This is the homogeneous piece, believe it or not. And this is going to be, hopefully, my particular solution. So let's see. I went a little fast, but I know you can easily separate the variables and solve, okay? So that's the homogeneous piece. Now, the particular solution, you might guess a linear function like at plus b. That's not going to work out for you. And the reason it doesn't work out is because of this piece. But you know it's a polynomial. So if a linear piece doesn't work out for you, you got to guess a quadratic. And if a quadratic doesn't work out, you could move up the ladder. I knew this probably would work because I have one derivative, okay? And if you differentiate once, second order quadratic, you will get linear, and we want linear, okay? So I am going to guess at squared plus bt plus c, which means its derivative of it is this. I don't need y double prime. I plug them in. This is y prime plus 2 over t, y is given, equals the forcing term. I multiplied here, okay? And I gathered my pieces. I got 4at plus 3b. I didn't write this, but 2c over t equals nothing, so that means there is no c. Okay, so I skipped it. There is no c here. So 2at plus 2at is 4at. b plus b is 3b equals t minus 1. So a is 1/4 and b is negative 1/3. Plug them back in here. You get 1/4 t squared minus 1/3 t plus 0. And that is, my good friends, the other piece. So the integrating factor turned out to be a much simpler method on this problem. But I noticed this and I thought, you know what, let's just do it, okay? So that's the purpose of this page, okay? Sorry I erased the 5th page. It's just some silly examples. But that should, I hope this is helpful in knowing how to use the integrating factor to solve ODEs of this type, all right? I'll talk with you later. Bye-bye.